Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. This is guided notes number 7 in the series on section 2.5b, Radical and Absolute Value Equations. The main idea in this section, as far as solving radical equations is concerned, is going to be to cancel them using exponents. However, we must keep in mind that squares and square roots, for example, are only imperfect inverses of each other. By that, what I mean is that if you take a negative number and you square it, but then you take its principal square root, you get its positive back. Another way that we can see that this would cause problems is if I started out with an equation like x is equal to 2, but then squaring both sides and following the square root property, I would wind up with two solutions, plus and minus 2. But one of these solutions, minus 2, we actually know in this particular example isn't true because we started out knowing what the answer really was. In other words, if I were to substitute minus 2 into the original equation, it wouldn't make sense. This kind of toy example and this property shows us that we have to be careful when we use squares and square roots as inverses of each other. And in general, this is going to be true whenever we have even indexed radicals and we're looking to cancel those. The source of this issue could be seen as geometric in the sense that when I have an even exponent, like a square or a fourth power, and I take a look at its inverse as a reflection over the y equals x line, what we wind up with is actually a multi-valued map and not a function at all. So how do we take all this into account? We are going to use the square root property. We are going to use the idea of canceling square roots with squares, but we're going to need to go back and check the answers that we get to make sure that they would have satisfied the original equation. Let's take a look at this first example. We begin by isolating the square root, minusing 10 from both sides, dividing by 5. We find the square root of this something is equal to 3. Now squaring both sides and solving, we wind up with the solution of x is equal to 7. Is this in fact the case? Well, yes. If we plug this back into the square, we're going to see that we have the square root of 9, which is 3, times 5, which is 15, plus 10 is 25. And in general, we're not going to have to worry too much about squaring square roots. In this case, the square of a square root will be x. It's the other direction where we have imperfect cancellation. That is to say, the square root of a square is only x when we know that x is positive. But that could still cause problems with our radical equations, even though we have this kind of nice cancellation for radicals. And the reason for that is going to be because if there is not just a radical of x, if we also have x's outside, then when I square both sides to get rid of this radical, what I'm going to wind up with is a quadratic equation. For example, here, setting equal to 0, we have x squared plus x minus 56, and if we factor that, we get two solutions. We get x plus 8 and x minus 7. And this gives us two answers, a x equals minus 8 and an x equals positive 7. And we'll need to check both of these to make sure that they're actually true. For example, if I plug in negative 8, the original equation would say negative 8 is equal to 56 plus 8. Now 56 plus 8 is 64, but the root, the principal root of 64 is positive 8. And that's of course not true. So what we've discovered is that minus 8 was not a solution. On the other hand, if we try 7, 56 minus 7 is 49, and the principal root of 49 is going to be 7. And so this one worked. Let's see if we can understand what's going on in a graphical sense as well. Here I've opened up a graphing calculator. If we take a look at one side of the equation, we'd have x. If we take a look at the other side of the equation, we have 56 minus x. And we can try to take a look at these two curves to see where they intersect. Now we notice that we have one solution here at 7. Indeed, the square root of 56 minus x is equal to 7 when x is 7. On the other hand, we can look just to the left to see that there is no intersection at minus 8. This was a fictitious solution that was introduced by squaring both sides. Let's continue. By squaring both sides, we get minus 44 plus 15x is equal to x squared. Moving this all over to one side and factoring, we'll need x minus, and an 11 and a 4 here to fully factor. This gives me two solutions. X is equal to 11 and x is equal to 4. Let's test these solutions in our equation. Is 11 equal to the square root of minus 44 plus 15 times 11? Well, 15 times 11 is 165, and subtracting 44 from that, I get 121. And indeed, 11 is the square root of 121, because 11 times 11 is 121. So that solution worked. What about 4? Is 4 equal to the square root of negative 44 plus 15 times 4? And in this case, we have another correct answer, because this is going to give us 60 for 15 times 4, and negative 44 plus 60 is going to give us 16. And we do indeed then have that 4 is equal to the square root of 16. So both solutions worked in this case. What was the difference? If we take a look at the graph of these two equations, we can see that the y equals x line, in fact, intersects the curve square root of minus 44 plus 15x in two places. We have an intersection at 4 and an intersection at 11. So really, these two solutions were both going to be true. We proceed in a similar fashion with the next problem. We want to take the square root and get rid of it by squaring, but first we need to isolate it, which requires us to minus 3 to the other side. This is going to give me square root of 5x minus 15 is equal to x minus 3. Now, squaring both sides, we'll have to square x minus 3. This will give us 5x minus 15 is equal to x minus 3 squared. We need to expand this and collect like terms. So let's just either use the perfect square formula, or you can write it out and FOIL. But this will give us x squared minus 6x plus 9 is equal to 15x minus 15. And bringing my 5x over to the other side, we get x squared minus 11x. And bringing my 15, I get plus 24. Now factoring, this will give me a minus and another minus. And factors of 24 with a sum of 11 are going to be 8 and 3. And so this gives me solutions at x equals positive 8 and 3. Or I should say, this gives me potential solutions. We still have to check that these make sense. Plugging in 8, we get the square root of 5 times 8 minus 15 plus 3. Is that equal to 8 itself? Let's find out. This would give us 40 minus 15 plus 3 is equal to 8. And that's the square root of 25 plus 3 is equal to 8. But this is 5 plus 3. And I think that's a good place to stop. We can see 5 plus 3 is equal to 8, so this is a solution. What about 3? Well, plugging in 3 here, we wind up with 5 times 3 minus 15 plus 3 is equal to 3. Well, 5 times 3 is 15, so this is actually just 0. And then we definitely get 3 is equal to 3, so these are two actual solutions. For the next problem, we're going to want to proceed by isolating the square again. If we bring this minus 9 over to the other side as plus 9, we wind up with the square root of x minus 3 is equal to 9 minus x. Now, I want to square this to get rid of it, which means squaring this side. If I square 9, I get 81. Twice the product of these two will give me minus 18. And then squaring negative x will give me plus x squared. This is the perfect square formula. Now, if I bring the x minus 3 to the other side, I minus x from minus 18 to get minus 19x. If I add 3 to 81, I'm going to get 84, and I've written things in descending order as my preference. We're going to want to factor this, so we set up our parentheses, x minus and then an x minus to give me this plus. Factors of 84, we have 84 and 1, we're looking for a sum of 19, and we'll make it pretty far down our list. You know, here's I have a sum of 20. As luck would have it, 84 divides by 7. 7 and 12. So this is going to be our two roots here. Let's see if either of these are solutions. So plugging in 12, we wind up with 12 minus 3 square rooted. 12 minus 3 is 9, and square rooted gives me a 3. Now 3 minus 9 is minus 6. That's not what the negative of what we started with, which was minus 12. And so 12 is not a solution to this equation. 7 minus 3 minus 9 is going to give me the square root of 4 minus 9, which is 2 minus 9, which is negative 7. Now that is the negative of what we started with. So that's going to be a solution for this equation. Here's a fun one. Let's approach this using substitution. If I take x plus 4 and set that to u, this says where's the square root of u equal to u? Squaring both sides, that's where we're going to be where u is equal to u squared. Subtracting this over, we have this is where u squared minus u is equal to 0, or where u times u minus 1 is equal to 0. This gives us solutions at u equals 0 and u is equal to positive 1. Reversing our substitution, we get x plus 4 is equal to 0, which gives us a solution at x equals minus 4, and x plus 4 is equal to 1, which gives us a solution at x equals minus 3. Alternatively, we also could have simply squared both sides here, which would give us x plus 4 is equal to x plus 4 squared. Distributing, foiling this, we would get x squared plus 8x plus 16. Subtracting our x plus 4 term over, we would wind up with x squared plus 7x plus 12, which factors x plus 4 times x plus 3, and gives us the same two roots in the end. Now, are either of these solutions, or are both? Let's plug it in and find out. Plugging in minus 4, I get 0 for minus 4 plus 4, and is that equal to minus 4 plus 4? It surely is. 0 is equal to 0. So minus 4 is a solution. Also, we have that the square root of minus 3 plus 4, which is 1, is equal to minus 3 plus 4, which is also 1. So both of these are solutions. Here, the square has already been isolated, so we can begin by squaring both sides. 8 minus 7x squared is then equal to minus 2 plus 3x. Now, 8 minus 7x squared, foiling this, will give us 64. Twice the product of the middle terms, which is 56. 56 times 2 is going to give me 112. So we get a 112x in the middle. And negative 7x times negative 7x is going to be positive 49x squared. This is all supposed to be equal to minus 2 plus 3x. We continue by grouping like terms, setting the equation equal to 0. Let's reorganize things. 49x squared. If I bring the 3 over, that's minus 115x. And if I bring the minus 2 over, that's a plus 2, which will give us plus 66. This is 6 times 11. This is 7 times 7. So we're not going to be able to reduce this in any way. Let's attempt to factor. I would put a 49x in both places. I would put a minus and a 1 over 49 out front for balance. Now, 49 times 66 is something I'm going to do on the calculator because I'm feeling particularly lazy this morning. We get 3,234. We're looking for factors of this that sum to be 115. Let's not start at the lower part of the list because that's going to take us forever. Let's consider 49 and 66. Hey, 49 and 66 actually sum to give me 115. So we really need look no further than these two. This gives me a 66 and a 49 to plug in here. And factoring out 49, we then have 49x minus 66 times x minus 1 equal to 0. This gives me two roots, one at 1 and 1 at 66 over 49. Let's check out both of these. 8 minus 7 times 1 is equal to 1. Is this equal to the square root of negative 2 plus 3 times 1? It sure is, because 1 is equal to the square root of 1. So this is an answer. And what about this peculiar looking thing? We have 8 minus 7 times 66 over 49. These cancel to sevenths, and so we have 56 minus 66 sevenths. That's minus 10 sevenths. On the other hand, on the other side, we'll have the square root of minus 2 plus 3 times, well, some number bigger than 1 here, 66 over 49, and we can immediately infer that this is not going to work because this is going to give us a positive number. And we have a negative number on this side, so we can stop. This is not going to be a solution. Now we're getting into some other kinds of radicals. The main idea here is that to get rid of one of these fractional exponents, we're going to want to raise it to the power of its reciprocal, which is 6/7. We want to do this on both sides, 2187 to the power of 6/7. Now, curiously enough, we should probably try to take the root of 2187, the seventh root of 2187. Now, once we take its seventh root, we could raise it to the sixth power. And in fact, we could have proceeded to just enter in, if we were using a calculator like this, we could have entered in the 6/7 power right here, or we could just now take 3 and raise it to the 6th power to get 729. So here on this side, we have x is equal to 729. For this next one, we want to use the same trick. We want to take x minus 3 to the 7/3, and we want to raise that to the 3/7. We want to do this to both sides, so 128 also raised to the 3/7. Reciprocal powers will cancel each other because we're looking at the product of powers when we take a power to a power, and a number times its reciprocal is 1. So this gives us x minus 3. Now, the seventh root of 128 is going to be 2. And so this gives us 2 to the third, which is 8. Adding 3 to both sides, we wind up with x is equal to 11. Here we have a fractional power which is not isolated. We begin by isolating that power. 4x to the 4/3 is equal to 64 then, and dividing by 4 on both sides, we wind up with x to the 4/3 is equal to 16. We then raise both sides to the 3/4 power, and these cancel, giving us x. 16 to the 1/4 power is 2, and 2 to the 3rd power is 8. So we wind up with 8 in this case. For dealing with absolute values, we want to keep something in mind. If I know that x in absolute value is equal to some positive constant, then this could happen in one of two ways. Either x was equal to that positive constant, or it's negative, because the absolute value of a negative would give me this positive. If x in absolute value is equal to 0, this can only happen if x is equal to 0. And if x in absolute value is equal to some negative, well, actually, let's just say a c less than 0. Actually, this cannot happen because absolute values only give positive or perhaps 0 values, but they cannot be negative. So if we were to isolate the absolute value and get a negative, we'd know we could stop and simply say there is no solution to such an equation. Here, we want to isolate by moving the 9 over first. This gives me 2 times the absolute value of x is equal to 2. Dividing by 2, we have x in absolute value is equal to 1, which means x could be equal to 1, or it could be equal to minus 1. Here my absolute value is already isolated, so we know this could happen if negative 3x plus 3 was equal to 15, or if minus 3x plus 3 was itself equal to minus 15. Then its absolute value would also be 15. We solve these two equations in parallel. We're going to commit the same moves for solving both of them, and we follow all of our sign rules appropriately. Hence, we have these two solutions. X is equal to negative 4, and x is equal to positive 6, which would make this work. You could check this, plugging them in if you like. This would give me positive 12 for negative 3 times negative 4, plus 3 is 15, or negative 18 plus 3 is negative 15, which absolute value would be also equal to 15. Let's begin by isolating this absolute value, dividing on both sides by 8. That gives us absolute value of 6x minus 3 is equal to 3. And this gives me either that 6x minus 3 is equal to minus 3, or that 6x minus 3 is equal to positive 3. Either one of these would give me an absolute value of positive 3. Adding 3 would give me 0, and dividing by 6 is also 0. Adding 3 would give me 6, and dividing by 6 is 1. So these are our two solutions. Here the radical is not yet isolated. We want to first add 2 to both sides, which gives me 27. But now I'm dividing off this minus 3. Dividing by minus 3 produces an absolute value of negative 7x minus 7, which is equal to negative 9. This has no solution. Once we have an absolute value equal to a negative, we can stop. Here I still want to start by isolating the abs val. This gives me 3 times the absolute value of 2y plus 3 is equal to 15. Dividing off my 3, we get the absolute value of 2y plus 3 is equal to 5. And so we either have 2y plus 3 is equal to 5, or 2y plus 3 is equal to negative 5. Solving these by minusing 3 from both sides, we then have either that 2y is equal to 2, or that 2y is equal to minus 8, giving me solutions of 1 or -4 respectively. Finally, we begin by isolating the absolute value. Minusing 8 from both sides gives me 4 times -13 absolute value minus 14 over 15x. K is equal to -4. But dividing by 4 to complete the isolation, we then have this -13 minus 14 over 15k absolute value is equal to -1. Again, an absolute value equal to -1 is a dead stop. This will have no solutions because absolute values cannot be negative. All right, that's going to be it for this video. Thank you very much for your patience. Have a great day and good luck with your studies. I'll see you in the next one.